Look at a modern pharmaceutical filling line or a semiconductor wafer fab. You are looking at an environment where perfection is the operational baseline. A single production batch moving across these lines routinely exceeds $100,000 in finished product value. Yet the integrity of that massive investment does not lie on the conveyor belt. It lies upward, completely dependent on the continuous flow of the unseen air passing through sealing grates. Governing bodies like the FDA and ISO do not offer suggestions for air purity. They mandate strict mathematical thresholds that dictate whether a facility is legally permitted to operate. This creates a critical operational vulnerability. A single microscopic breach in a filtration system, completely invisible to human eyes, registers to an auditor as a catastrophic contamination event. Preventing these quiet six-figure failures require us to abandon intuitive assumptions about how air filters work and examine the actual fluid dynamics of particle capture. High-end manufacturing is, at its core, an exercise in microscopic risk management. The most common misconception is that HEPA filters operate like a kitchen sieve, acting as a simple physical net catching debris. If true, tiny pathogens like viruses would easily slip straight through the open gaps in the material. This diagram reveals absolute filtration's true architecture, a chaotic, microscopic fiber web manipulating fluid dynamics. First, impaction. Large particles possess too much energy to navigate twisting currents, slamming directly into fibers. Second, interception. Mid-sized particles follow curved airflows but graze fiber sides, snagging permanently. But particles under 0.1 microns stop obeying aerodynamic rules entirely. Lacking significant mass, they suffer constant random molecular bombardment, known as Brownian motion. This erratic zigzag path dramatically increases their odds of eventually striking a fiber and locking in place. HEPA filtration functions as an engineered probability matrix, where even the most elusive particles eventually collide with a fiber surface. The development of absolute filtration began far from the needs of modern medicine or microelectronics. As this historical marker outlines, the technology was spearheaded during the Manhattan Project, specifically to capture and contain lethal radioactive dust. This photograph shows the pioneers of those early cleanrooms. To ensure these hoods were secure, engineers needed a rigorous way to validate the air barriers. For 50 years, the industry relied on DOP. Technicians generated a thick mist of this liquid plastic, spraying it into ductwork to challenge the filters. Eventually, safety agencies like the EPA and OSHA intervened, flagging the DOP aerosol as a potential health hazard to the personnel conducting the tests. Facility managers had to find a new testing agent that maintained regulatory compliance testing without compromising worker health. The solution was PAO, or polyalpha olefin. It provides the exact same aerosol challenge capabilities, but with a significantly safer chemical profile. Today, PAO is the absolute gold standard for testing in modern American manufacturing facilities. The validation procedures represent a carefully balanced compromise between absolute environmental security and human safety. Because the target particles are subvisible, theoretical physics on a whiteboard is insufficient. The integrity of the facility must be empirically proven on site. This schematic illustrates the first step of modern validation. Technicians artificially challenge the system by pumping a massive, known concentration of PAO aerosol directly into the upstream airflow. This upstream challenge acts as an extreme stress test, forcing millions of microscopic particles directly against the probability matrix of the filter fibers. To verify the capture rate, technicians deploy a primary diagnostic tool on the downstream side, known as a digital photometer. The photometer functions like a highly sensitive, laser-based smoke detector. It pulls in air and calculates the exact concentration of individual escaped particles. This reading is governed by the strict mathematical limits of the US ISO 14644-3 standard. If the instrument detects more than 0.01% leaking through, the environment immediately fails compliance. Modern compliance mandates the identification of a failure's exact physical coordinates, rather than a simple calculation of total leakage. Every square inch of the filter media must be manually scanned, with intense scrutiny directed toward the outer perimeter frame. A perimeter seal leak is particularly dangerous. It creates an open bypass channel, allowing contaminated air to flow straight into the room, entirely evading the fiber web. None of this data matters if the equipment is inaccurate. Raw readings are entirely invalid unless the instrument is calibrated to a known national standard. By maintaining calibration to the NIST standard, technicians secure objective data. Skipping this step turns precision safety reporting into expensive, indefensible guesswork. A properly executed ISO 14644-3 scan is the only legally defensible proof that a clean room's filtration physics are actually functioning in reality. Modern technological and medical output depends on maintaining a capture efficiency that permits no more than 0.01% penetration. This historical photo captures the massive scale of pharmaceutical distribution. Securing outputs of this magnitude requires controlling an environment down to the movement of single sub-micron particles bouncing through a fiber web. Rigorous NIST-calibrated scanning remains the primary defense against localized bypass leaks that can compromise millions of dollars in inventory. Hoping for the best is not an engineering strategy. Continuous empirical validation is the strict requirement to keep these vital supply chains flowing. If you work in facility management or certification, drop a comment below. What is the most complex or unexpected leak path you've isolated during a routine scan? Keep your environments pure and your science tight. See you in the next one.